Arc of charge. We have a negative charge distribute uniformly around a wire arc of radius 0.15 meters. So that's this right here. It has a linear charge density lambda, and theta is equal to 45 degrees. There's my theta. Determine the total charge on the wire. What is the magnitude and direction of the electric field at point O, the origin right here? Then you place an electron at point O. What is the magnitude and direction of an external force that must be applied to keep it at rest? Ignore the effects of gravity for parts C and D. Then D, the external force from part C is removed. Describe the initial motion of the electron. After a long period of time, how has this motion changed or stayed the same? Determine the total charge on the wire. We're going to use our definition of linear charge density. Lambda is total charge over L, and then just rearrange that so Q equals lambda L. So we know what lambda is, but we now have to find the length of the wire. So the way we're going to do that, we know that it subtends an angle of 90 degrees, and we're going to call that phi. It's equal to 2 theta, pi over 2 radians, 90 degrees, and then we'll find Q from that. So we know that the length, and that's equal to r phi, right? That's whenever you have a segment like this. If this is phi, this is r, this is r. This length here is just going to be r phi, right? That's the definition of a radian. So that's equal to 2 theta, and here's r, 0.15 meter, 2 times theta. Theta is pi over 4 radians, so we get 0.236 meters. So I can now plug that length into this equation right here, and I have negative 3 times 10 to the minus 6 coulombs per meter times 0.236 meters, and I find my total charge is a negative 7.1 times 10 to the minus 7th coulombs. What is the magnitude and direction of the electric field at point O? So what we're going to do is pick 2 points on the arc that are opposite each other and draw the electric field at point O due to them. So let's just start, we'll take the endpoints. Okay, so we have 1 point over here, 1 point over here. The electric field at point O points towards the charges, just like this. And then we add them together, and hopefully you can see that the y components cancel out because we have the same little dq, little bit of charge anywhere on this arc. And the only components we have are in the negative x direction. And then you can keep going, right? I picked the 2 points on the end, now pick 2 points like this, then 2 points like this, and finally a point here where obviously electric field is all in the negative x direction. So our direction of the electric field at this point O is in the negative x direction. Now we're going to find the magnitude. What we're going to do is pick one dq, one little piece of the ring right up here, okay? We'll calculate the electric field due to it and then integrate over all of them. So what we'll do, we'll find dE due to the one charge, and then we've already shown that the only electric field that survives is in the negative x direction. So dEx will be the magnitude of dE times cosine theta, and you can see where we're measuring theta from. So let's start. dE is k dq over r squared. Okay, that's just kind of the definition of the electric field, right? Let's just put it there due to a point charge. And we're considering this dq a point charge. But what is dq equal to? Well, we have q is equal to lambda L. So dq would just be lambda dL, right? Just take the differential. And since lambda is a constant, that comes out in front of the dL. So we're getting closer here, but we've got theta, and here I have this dL. Can I express dL in terms of theta? Well, sure. And let's draw that picture. Here's the arc. Okay, this is r. This over here is d theta, and this will be dL, right? That's the arc length subtended by d theta. So dL is r d theta. And you can see what we did there. We got rid of the dL and it's r d theta. We still have it over r squared. And then our last step here, dEx, is dE times cosine theta. Okay, so I have dE, which is k lambda r d theta over r squared. You can see how this r is going to cancel one of these. And then the cosine theta comes in here. So dEx is k lambda over r times cosine theta d theta. The key is to get all your variables and your differential the same, right? So that's why we made the switch where we went from dl to d theta. Now we will sum up the contributions to the electric field by integrating dEx from theta equals 45 degrees to theta equals minus 45 degrees relative to the negative x-axis. So we're going to start here and integrate around in that direction. So you can see our first angle here will be 45 degrees. We'll pass through 0 and go over here to where it's negative 45 degrees. So what do we have? Here's our dEx. We're going to have the total electric field. We'll integrate from, again, 45 to negative 45, k lambda over r, cosine theta d theta. The integral of cosine theta, of course, is sine theta. We pull the k lambda over r out in front. We evaluate it between negative 45 and 45, and we get an electric field of negative square root of 2 times k lambda over r. With the chosen order of integration, I mean, we went this way. You could just as easily have gone the other way. The value of the electric field is negative, seemingly indicating it is pointing to the left, as our geometric proof showed. Had we reversed the limits of integration, it would have shown a positive number. So there's no real significance to the sign obtained. We find the direction by doing that bit of vector analysis, and then we found the magnitude by doing the integration. So our answer is the magnitude is the square root of 2k lambda over r, and it's in the negative x direction. An electron is placed at point O. What is the magnitude and direction of an external force that must be applied to keep it at rest? And we're going to ignore gravitational effects. So let's start with our electric field. And perhaps this makes you a little uncomfortable because we're showing the magnitude of the electric field is this, and then I tacked on the direction. Well, that's just the limitation of high school physics, because the nice way to write this really is electric field equals minus square root of 2k lambda over r I hat. Okay, there you go. That's magnitude and direction all in one nice little vector expression. So here's your magnitude, and we're just tacking on the direction just to show you. Now the arc's electric field is in the minus x direction, so the force it will exert on an electron at point O will be in the positive x direction. Remember, the electron moves opposite the electric field, right? A positive charge would move with the electric field. So what do I need? I need an external force in the negative x direction of equal magnitude when added to the arc's force will result in a net force of 0 newtons. That will keep the electron at rest. So let's find the magnitude of the force now. The force is just going to be Q times E. So I've got my expression here. Here's the charge on an electron. Here's K. Here's lambda, which we found earlier on. And here's my R, the radius of the semicircle. You plug all the numbers in, and you get a force of 2.7 times 10 to the minus 14th newtons in the negative x direction to hold that electron immovable. We now remove the external force from part C and describe the initial motion of the electron, position, velocity, and acceleration. After a long period of time, how has this motion changed or stayed the same? And again, ignore gravity. Initially, the electron will move in the x direction, okay, because that's the direction of the force on it, with its maximum acceleration and the minimum velocity, right, because you started at rest. After a long time, the electron will continue to move in the x direction with a decreasing acceleration, because that's a function of 1 over r, but with a constantly increasing velocity. So the rate of velocity increase will decrease. Well, that's a tough sentence. But the velocity will keep increasing. In other words, it keeps going faster, just not at a rate that it did in the beginning. Just because the acceleration is decreasing doesn't mean the velocity is. Please don't confuse that. So the acceleration decreases, the velocity continues to increase.